Okay, for this lesson we're going to be talking about graphs of equations, and this is section 1.2 in your text. What we're going to learn today is how to sketch graphs of equations, how to find x and y intercepts of graphs of equations, how to use symmetry to sketch graphs of equations, how to find equations of and sketch graphs of circles, and how to use graphs of equations in solving real-life problems. Now, a lot of this is review, sketching graphs of equations and finding x and y intercepts of linear functions. You should have learned in Algebra 1, finding x and y intercepts of quadratic functions. You should have learned in Algebra 2. Using symmetry to sketch graphs of equations, you should have learned a little bit in Algebra 1 and more in Algebra 2. Graphs of circles, I think that was geometry in Algebra 2. So again, a lot of this should be review. So graphs of equations. Remember, we have graphical representations for functions. We have verbal, we have algebraic, we have numeric, and we have graphical representations. So graphical representations use two variables to represent two quantities that the equation compares. And usually this is x and y. Each point on our graph is a solution to the equation. That means that each point creates a true statement when it is substituted in for its designated variable. Okay? And that true statement is the left-hand side of the equation equals the right-hand side of the equation. The graph is a set of all the points that are solutions to the equation. Okay? So since there's infinitely many solutions, there will be infinitely many points on that graph, and they'll all have specific shapes, and those specific shapes are what categorize the various equations into our function families. So, we want to determine whether these 2 points are solutions to the equation y equals 4x minus 2. This is a very easy thing to do. We're just going to say, hey, we know that our points are x comma y, so we can substitute in. So if we have y equals 4x minus 2, and our y value is negative 4, and our x value is positive 2, then I should get that negative 4 is equal to 8 minus 2. Now 8 minus 2 is 6. Negative 4 is not equal to 6, so it is not a solution to that equation. Let's check the other point. We have y equals 4x minus 2 again. My y is a 10, and we have 4 times 3 minus 2. Well, 4 times 3 is 12, minus 2 is definitely 10. So it is a solution because this is a true statement. Okay? Sketching graphs of equations. The easiest way, and this is something that works for all equations, is to plot points. We have an x column, we have a y column, and we try to figure out for any given x or y what the other variable is, and that creates our points. So to do this, we're going to rewrite the equation so that the equation is solved for one of the variables. Doesn't matter which. If possible, usually we solve for y. We're going to make a table of values. This table is going to be like x comma y, or x f of x, or something to that effect. And those points, say we know that x is 1, we can solve and get f of x is 0. That creates the point 1 comma 0. And then once we get several of them and we can see the shape of our function or our equation, we can connect the points with a smooth curve or a line because we know that there are infinitely many solutions, and they'll be jam-packed together and they'll end up looking smooth anyways. So let's sketch the graph of y equals negative 4x minus 7. So we have an x and a y. This is already solved for one variable. So we're going to try to maybe sketch negative 2, 0, and positive 2. So if I let x equal negative 2, y will equal negative 4 times negative 2 minus 7, which is 8 minus 7, which is 1. So we'll have the point negative 2, 1. If, and do another little thing here, if x is 0, that would be y equals negative 4 times 0 minus 7, which is just going to equal negative 7. So my point is 0, negative 7. And if y is or if x is positive 2, y will equal negative 4 times positive 2 minus 7, which will be negative 8 minus 7, which is negative 15. That's not going to fit on this graph, right? But the other points do. We could try maybe negative 3. That might be a good point. So y equals negative 4. Hold on, that's way too messy. Y equals negative 4 times negative 3 minus 7. So that's going to be 12 minus 7, which is 5. So we have the point negative 3, 5, which is right here. We have the point negative 2, 1, which is here. And we have the point 0, negative 7, which is here. And we can see that these all definitely form a straight line. And so that's our equation. And you can do this with any function. Here's another one. Y equals x squared minus 2x plus 1. So we're going to have an x and a y. And I'm going to try negative 2, 0, and 2 again and see what kind of data that gives us. So y equals, hold on here, negative 2 squared minus 2 times negative 2 plus 1. So that's going to be 4. Plus 4 plus 1 is 9. And for y equals 0, that is 0 squared minus 2 times 0 plus 1 will equal 1. And for 2, y will equal 2 squared minus 2 times 2 plus 1. And that's going to be 4 minus 4 plus 1, which is 1 again. So now we can kind of see where our symmetry is going to be if we were using symmetry. So we have the point 0, 1, and the point 2, 1, and the point negative 2, 9. Okay? So we can see that halfway in between x equals 0 and x equals 2 is going to be our vertex. So why don't we try x equals 1, and that's going to be y equals 1 squared minus 2 times 1 plus 1. So that is 1 minus 2 plus 1, which will be 0. Okay, and then using symmetry, we can see that we'll have this point here as well, which gives us our nice, if I could draw a better parabola. So intercepts of a graph. Intercepts occur when a graph of an equation crosses either axis on the coordinate plane. When we're finding intercepts, and this is a very easy thing that you did back in Algebra 1 and Algebra 2 for finding intercepts, for our x-intercept, we let the opposite variable y equal 0, and we solve our equation for x, right? So we want to know where on the x-axis does it cross. We know to cross the x-axis, we have to have a y equals 0 value, which is why we let y equal 0. Talking about the y-intercept, we want to know where on the y-axis it crosses, and any point on the y-axis is always going to have an x equal to 0, and so that's why we let x equal to 0. Okay, so let's find our x and y intercepts of this equation. And this will be a little bit more difficult because it is a cubic equation. So let's try to find, first of all, our y-intercept, because that's the easiest, at least for this one. So we let x equal 0, right? And that would just be y would equal 0, because if I plug 0 in here and I cube it, minus 2 times 0 plus 0, that's just going to be 0. So we've got that point, easy peasy. Now, the x-intercept, a little bit different, because we have to let y equal to 0. Okay, now if we let y equal 0, then we have 0 equals x cubed minus 2x plus x. And we have to think about factoring, right? Each of these terms has a GCF of x, so I can undistribute an x, so I'm left with x squared. This should have been a 2x squared. Typo there. Minus 2x plus 1. Okay? And we have to look at this even further and see, do we have anything that we can factor with this trinomial? And if you think back, I'm going to have two binomials, right? The first one is going to be x, the other one's going to be x. And 1 times 1 is 1. This sign is positive, so each of these two signs will be the same. And this tells me, this sign here tells me that each of these will be negative. Okay? So that means my x-intercepts are going to be x equals 0 and x minus 1 equals 0, so x equals 1. So my y-intercept is the point 0, 0. My x-intercepts are the point 0, 0, of course, and the point 1, 0. Okay? So recall that when we have a repeated factor here that is also an intercept, what this means is the vertex is actually happening at this point 1, 0. Okay, so now let's talk about symmetry. There's three different types of symmetry. First of all, we have x-axis symmetry. This is happening when we can fold our equation across the x-axis. And this happens whenever a point, x comma y, and x comma negative y are both on the graph. Okay? So, same x value, two different y values, each the same distance away from the x-axis, one on top, one on the bottom of the x-axis. Y-axis symmetry happens when we can fold an equation across the y-axis. And the y-axis is the vertical axis. And so if we want to fold our equation across the y-axis, we're going to have positive and negative values of x, okay? So this means that the 2 points are equal distance away from that y-axis, but on either side of it. One on the positive side, one on the negative side. The third type of symmetry is origin symmetry. And this is when you can rotate something 180 degrees. Okay, this is when you cut it at the origin, okay, and you rotate one half of it 180 degrees and it'll lie exactly on top of the other half, okay? And algebraically, this happens when, or graphically, this happens when a point, xy, and a point negative x, negative y, are both on the graph. So to give you an idea of what this looks like, if I have a sine curve here, okay, and I cut this sine curve right here at the origin, and I rotate this part of it around, it would lie directly on top of this part over here, okay? So algebraic tests for symmetry. We talked about this with respect to how it looks on a graph, but here's how we do it algebraically. So if we're trying to test if something is symmetric with respect to the x-axis, we want to replace our y with a negative y and see if we get the same equation. If we want to test to see if an equation is symmetrical with a y-axis, we'll take our equation and replace that x with a negative x and see if we get the same equation that we started with. And the third test is to see if something is symmetric with the origin, and it just kind of combines the two previous tests. So we replace x with a negative x and y with a negative y and see if we get our starting equation after we simplify everything. So let's take a look at what this is going to look like later. Okay, let's talk about how to use symmetry with sketching. So we want to use symmetry to sketch the graph of x squared plus 2, okay? Now, I am going to noticing because I know a little bit about Algebra 2, I know a little bit about geometry, so I'm taking an x squared and I'm raising it up 2, right? Well, all I really have to do is graph 1/2 of this. So how about I take 0, 1, and 2? Well, 0 squared is 0 plus 2 is 2. 1 squared is 1 plus 2 is 3. 2 squared is 4 plus 2 is 6. So I have the point 0, 2, 1, 3, and 2, 6. I can just mirror those across that y-axis because I know my parabola shape is symmetric with respect to the y-axis in this instance, okay? Now let's talk about circles. And by the way, when we were talking about algebraic tests for symmetry, we are going to cover that in class, and you'll get to have a lot of chances to do that in class. Let's go back and review circles first, though. Standard form of an equation of a circle: x minus h squared plus y minus k squared will equal r squared. And that is given the fact that we have a center of h comma k and a radius of r. So what this looks like is, say I have x minus 2 squared plus y plus 4 squared equals, let's see, 20. My center would be the point 2 comma negative 4. And my radius would be the square root of 20, or 4 times 5, 2 times 2, I've got a pair of 2's, so that is 2 radical 5 once we simplify this. And yes, you are going to need to remember how to simplify radicals. So in this course, we're bringing together all of the different skills that you learned in your other courses. When we start preparing for calculus, this is preparing to have all these skills ready and at your disposal, because when we get to calculus, you're going to use them all, okay? So equations of circle. Given a center of 2 comma 3 with a radius of 4, find the equation of this circle. Okay, so we have the center is going to be x minus our h, which is 2 squared, and y minus our k, which is 3 squared, and 4 squared is going to be 16, okay? And we've already done this problem on the previous page. So applications. Okay, I know this is probably really small on your screen, especially if you're viewing this on a phone. So there's 4 ways to describe algebraic relationships. We have verbal, algebraically, numerically, and graphically. And we have a acronym for that called VANG. Okay? So runners can estimate their time to finish a race based on the results of a previous race and one of several prediction formulas. A commonly applied model is called Cameron's equation, which forecasts your next performance based on a previous race result. And the equation is T2, or the time for your second run, is equal to the time for your first run, times a ratio of the distances, so distance 2 divided by distance 1, times a ratio of this function with distance 1 and distance 2 put into it. So f of d1 divided by f of d2, okay? Now this function is the key to this whole race thing, okay? So this function is f of x equals 13.49681 blah, blah, minus 0.000303363x times 835.7114 divided by x to that power. Okay, and I have my little annotation down here as to where I got this online. I'm a runner, so this was kind of an interesting thing that applied to me. So I can take my first distance and plug it into this formula. I take my second distance and also plug it into the same formula. Okay, and that's what's going to go here. Okay, so let's take a look at what this will look like with an actual problem. First, what we have here is a graph of this f of x. And this is to kind of show you what this reciprocal function looks like. And we know that reciprocal functions typically exist in two quadrants, but because we're dealing with time here, we're only showing this in the first quadrant because this would also exist in the third quadrant if it were part of the domain of this function. But it's not. So we have, this is our formula, and it kind of shows here that, you know what, as you're looking at this, going from 5,000 meters to 25,000 meters, and taking your time down in minutes per meter or seconds per meter, then we can see how many seconds it takes you to run that many meters. As your distance increases, what's your average pace going to be? So if I ran 5,103 meters in 57 minutes and 23 seconds, how long will it take me to run 8,400 meters, which is 5.22 miles? Okay, so this is the difference between an actual run that I did and how long will it take me to run 5.2 miles. Okay. So using our formula, I've taken a few shortcuts here to kind of simplify this for us. I took a scientific calculator, one of the Inspires, and I plugged in this function here. Oops, plugged in this, no, I needed to do this. Plugged in this function here, and I found my two f values. So I wanted to find f of 5103, and that turned out to be 14.3212. And I found f of 8,400, right, because that's my second distance, and that was 13.9023. So those are two of the big numbers that I needed to plug into my formula to find my T2. So because my T2 formula was T2 equals T1 times D2 over D1 times f of D1 divided by f of D2. So when I plug all that in, that gives me 57.3833 plus 8,400 divided by 5,103 times my 14.3212 divided by 13.9023. So when we calculate all that out, that means my time is going to be 59.075 minutes. So if I want to run 3.17 miles in 57.38 minutes, then to run that doesn't make sense. And doing a little troubleshooting, I discovered my little error here. My little error was this is not supposed to be a plus. That should have been a times. So times, okay? And so when I make that a times, everything becomes nice again, because I couldn't run, you know, nearly twice as long in 2 more minutes. No, that just wouldn't happen. So that should be actually 97.3043 minutes would be my new time 2. So sometimes you have to take a look, stop, and see, hey, what did I do wrong with that problem? And come out with something really silly, usually copying something down wrong. Okay, so what we've learned how to sketch graphs of equations, how to find x and y intercepts of graphs of equations, how to use symmetry to sketch graphs of equations, how to find equations of and sketch graphs of circles. Actually, we didn't cover sketching graphs of circles, but we will cover that in class. How to use graphs of equations in solving real-life problems was something we also covered as well. So we will do this in class. And so that's it for today.